We'll move on to our next talk, which is from Rebecca Larson. And the talk title is Islands of Reionization. So Rebecca, when you're ready, go ahead and share your screen and you can unmute yourself and get going.
Thank you, Steve, and thank you, Steve, and the rest of the SOC for putting on this conference. I really appreciate the opportunity to give this talk, and I wanted to give another special shout out to all of my collaborators I've listed here, many of whom are at this conference, so a virtual hello to you. Can't wait till we can be at the next conference in person together. So today I'm going to talk about a program called the Islands of Reionization, which is a Keck program that I've been working on for the past couple of years now. And it's looking for high redshift galaxies. And so I'm just going to talk about the most recent results that I have and update everyone on where I'm at. So this program is looking for redshift 9 Lyman alpha emission. And that sounds like a very daring thing to try to do with ground-based telescopes, especially given the fact that this redshifts is where Lyman alpha ends up in the infrared. And so why are we trying to do this, and why do we think that we can do this? Well, there's a couple different reasons, and I'm glad I don't have to do a whole intro about reionization to this particular crowd. And so there's a lot we don't know about the reionization era. We don't know what the source of the reionization photons were, and we don't know exactly when it started or how quickly the process went forward. So here I'm showing a plot that has the ionized volume fraction, so how much of the universe is ionized on the y-axis, and then redshift on the x-axis. And so here we're showing two different theories and models of how reionization could have happened. And so this first one I'm going to show you is this gray line right here. And so this assumes a uniform escape fraction of ionizing radiation from every galaxy. And so what you end up having is you have high mass galaxies producing most of your ionizing photons, but it does take time to build up high mass galaxies. So this reionization process starts a little bit slowly, but then once you get big galaxies, you actually can ramp up and ionize a greater portion of the universe much faster. But if you assume that the ionizing escape fraction is actually halo mass based, then you actually have ionized photons escaping from low mass galaxies early on. And since there are more low mass galaxies, and because they are formed sooner, we are able to start this reionization process earlier, and it doesn't have to be such a drastic ramp up. And so the time in history in which these two different models are the most discrepant is redshift 9. And at redshift 9, one theory will predict that only 10 to 20% of the universe will be ionized, and then the other one would predict that 60 to 70% of the universe will be ionized. So if we assume that about 60% of the universe is ionized, we should be able to see Lyman alpha. And that is because Lyman alpha will resonantly scatter out of phase if the ionized bubble is large enough. And so if you have an ionized bubble that's about a megaparsec across, you would be able to see Lyman alpha along that line of sight. And so what we wanted to do was to target galaxies that we thought would be some of the ones that are in those ionized bubbles early on. And so we looked for high redshift galaxy candidates in the cosmos field. And this is a paper by Steve Finkelstein in prep for this year. And we looked for galaxies that have neighbor subtracted IRAC photometry. They were visually inspected. We checked for persistence and were very careful on all of the things that we were looking for. And so our final sample of galaxies is around 11 redshift 9 to 11 galaxies across all 5 candles fields. And we also looked for the ones that had high ionizing photon fractions because we looked for the Spitzer IRAC colors where the O3 would have been bright. And so we had red IRAC colors indicative of high ionizing radiation. These would be the galaxies that would be most likely to be in an ionized bubble because they are emitting enough of that high energy radiation. And so what we did is we targeted these galaxies. We got time on the telescope for 4 semesters, 2 nights each in 2018 and 2019. And then we also had 2 nights in 2020 through another program PI'd by Taylor Hutchinson. And so she will actually be talking about her portion of this science in our next session. So we used the Keck MOSFIRE spectrograph, which is a multi-object spectrograph. We looked in the J band, which is 1.15 to 1.35 microns, which corresponds to a Lyman alpha emission around 8.5 to 10.1. And so we can actually observe about 30 objects per mask, but we only have about 2 to 3 at maybe 5 if we're lucky of our redshift 9 to 10 objects that fit in one individual pointing. And so we actually filled the slits with some lower redshift 5 to 7 galaxies, looking for UV nebular emission lines like carbon-3 and carbon-4. And again, I will encourage you to watch Taylor's talk later today about that science. And so we also placed 2 stars in our slits so that we had a good understanding of where everything was lined up, and because we needed to be able to see something with continuum to make sure that we were having good observations and nothing was going wrong. So I have a list here of just all of the different observations that we took. So there's a known problem with MOSFIRE, and that is that over the course of a night, if you observe for long exposure times, you actually find that your objects drift in the slit. So from where they're expected to be in your detector, and if you expose for a long amount of time, they actually start to drift. So this plot that I'm showing here is over time. Some of our observations were over 6 hours. We are watching the drift of the object every 5 minutes. And so here we're looking at those stars that we put in slits so that we can measure this effect. And this is something that we had to incorporate into our data reduction on top of running it through the pipeline and making sure that we were aligning everything up and accounting for this drift, because we need every photon possible if we're trying to do Lyman alpha at redshift 9. And so we are using an offset relative to the first frame. And the reason I say relative to the first frame is because we also found that some of our objects were offset from where they were expected to be in the slit. From the position the pipeline says that this object should lie in your detector, it was actually off. And so in order to account for this, we came up with a different kind of extraction method. So here we use that slit star where you are getting a positive trace and 2 negative traces due to our dither pattern in MOSFIRE. And a continuum source would look like this model right here. And so what we wanted to do was boost the signal of real lines by using the profile of an actual line, including the 2 negatives as our extraction profile into a 1D spectrum. But the problem we found was that some of our objects were offset. And so what we needed to do, especially for those objects like redshift 9 Lyman alpha galaxies, where you do not detect continua, and you have to look for very faint emission lines, we wanted to make sure that we were looking at every possible position that our galaxy could be at. And so we took a look at all of the galaxies that we had as filler targets and our stars and brighter sources that we were able to detect continuum, and found that they were offset between -3 and 3 pixels from where the pipeline expected it to be. So here at the bottom left, I'm showing that same emission line at the top, but showing you exactly where the center is supposed to be in the pipeline, but also showing you that this bright blue line is actually where the center of the object is. And so it is offset from where the pipeline expects it to be. In order to account for this and to correct for this, we extracted with this weighted extraction profile at all 7 of these offsets for every single one of our galaxies for every night. You can see on the right here that when we actually line up our extraction profile, we get the full flux from our emission line. For this particular bright low redshift line, we would detect it no matter which offset we use. But when we line up the model with the correct center of our emission line and our galaxy, we get the full flux. And so this is exactly what we want to do for faint lines, is get the most amount of flux possible and be as accurate as we can. But like I said before, we don't exactly know where our object is in the slit if we can't see the continuum. So we did a rolling extraction and had 7 different centers for every time we observed a galaxy. And so sometimes we observed a galaxy 3 different times in order to get the total amount of exposure time we needed to potentially detect these lines. That means that for every night we had 7 possible spectra, and we had 3 nights, which is 343 different combinations for just one galaxy to try to find the line by matching them up. Thankfully, in 2018, I worked on an automated line finding code that I used to look for Lyman alpha at redshift 7 in the Hubble GRISM data. And I used that same code to automate a search for emission lines in every single one of these 343 spectra. And so what I looked for was emission lines that were greater than 2 sigma in any of the combinations. And then I looked for the combination where we found it with the highest signal to noise. So when we matched all of the offsets correctly, we get the total flux of the line that we detected. And so we also had to do away with the skylines. And so all of this process is quite detailed, but I'm going to skip over it for this short talk and just show you some of our preliminary results. So this result right here is a Lyman alpha emission line that would be at redshift 8.7. And so here on the left, I am showing just a Hubble image stamp showing the two slits that we had with different orientations for this object. A total exposure time of 9.5 hours for this over 3 different nights with an average seeing of 0.7 arc seconds. In fact, this is probably our best data that we got. And so I'm very happy that in our best data, we actually have a detection. I'm showing the IRAC postage stamps at the top where we do have that red IRAC color indicative of potentially strong O3 emission. And so our photo Z is around 8.9, meaning that we're doing a pretty good job of getting all of our photo Zs for our target galaxies. Here I am showing in the 2D the counts per second. So this is our data. And then here is a signal to noise of this same emission line. Like before in that example of the low redshift object, you would expect to see a very bright emission line in those pink circles, and then 2 negative traces in the teal circles. And to the right, I'm showing the extracted 1D spectra, where we find the line in both nights individually with our line finding code, but we also find the line at the same position in the stack of those 2 nights together. So I said I observed this night 3 times, but the night that we observed it with 1.3 hours was very bad seeing and was very noisy data. And so we decided overall, we're going to remove any one of our nights that have less than 2 hours of exposure time because they do not add to our science. So this is exciting in and of itself, but the more exciting part about this is that this particular object is physically very close to another redshift 8.7 galaxy that we already knew about. Zitrin in 2015 found this Lyman alpha emitting galaxy, and I've drawn this circle right here. Behind us is a stamp of the candle's EGS field. And so you can see that a lot of our targets here are in the EGS field, and the green squares are where we put our MOSFIRE pointings. We didn't look at Zitrin's object because we already have a redshift from it. And so we focused on getting data from some of our other candidate galaxies. What's interesting is our redshift 8.7 galaxy is over here. And if you do some cosmology calculations, you find that these 2 galaxies, given that they're at the same redshift, are only 3.5 megaparsecs away from each other in proper coordinates. What is also interesting is this object that we found Lyman alpha in 2015 was also found to have a nitrogen 5 emission line in 2018. And that means that there's probably an AGN, which would also increase the amount of ionizing photons that are escaping from this galaxy, potentially making the bubble around it much bigger. And so what are the implications for reionization from this detection and from our whole survey? Well, 2 of our 9 targets have tentative Lyman alpha detections, including this one from Zitrin in 2015. And since they're physically close to each other, there's potentially an overdensity in EGS. In fact, 5 of our 9 total candidate galaxies are in EGS, which is already indicative of a potential overdensity at this high redshift. And so overdensities would actually be the things that reionize first, which would make it much more likely for us to detect Lyman alpha. And so it's already a serendipitous detection of nitrogen 5 that includes even more ionizing photons, meaning this is even more likely to be an ionized bubble. We still have a lot of work to do. I'm not done finishing all of our data analysis, but I'm happy to announce that I am finally done with the data reduction. And so if we confirm this line, this could indicate large ionized bubbles as early as about redshift 9. So I'm going to leave that there and go ahead and take questions. Thank you.
All right, thank you, Rebecca. So the first question is from Sarah Bosman, who asks, are the MOSFIRE offsets between exposures you find consistent with the positions of other bright objects in the same slit as this galaxy?
Yes. So all of the offsets, when we did, we decided to do -3 to 3 pixels as our range of extraction centers because we looked at the objects that we were able to see in continuum in that same mask and found that they ranged from that range of offsets. And that's why we decided to use those as our extraction centers. Now, this also is a problem when we have contaminating sources and things like that. And so there's a lot of other things that I didn't include, but that was why we use those extraction centers.
Okay, and one last question from Ryan Ensley, who asks if you're willing to share the UV magnitude of the source.
The UV magnitude of this source, I believe, is 27-ish, but I will have to look up the exact number. I don't have that written down right now.
All right, that was a quick answer. So I'll give you one more from Dan Coe, who asked if your results help constrain the reionization histories that you showed back in your introductory slide.
So I am hesitant to kind of make that that broad thing without having looked at all of my data so far. I was still trying to go through all of that late last night. So with this one detection, I think it's interesting that we're seeing potentially this overdensity, and maybe that's just a serendipitous line of sight or a situation that worked out in our favor. But if we are able to constrain the likelihood of seeing something like this overdensity with some of the theoretical models, then we would be able to say how likely we were to have found this, and then maybe use that information to make an estimate of how much of the universe was reionized at this point.
All right, thank you very much, Rebecca.
Thank you.